Okay, so first you completed your investigation from Desmos, and there was kind of 3 ways, hopefully, that you could see you could tell something was an inverse, and that's numerically, graphically, and algebraically. So numerically, we're looking for this idea where the inputs become the outputs, and there's this switch between the two. So you see a switch of x and y values. So that meant that if I saw a chart for an original function and I had x's and the outputs for these, and let's say I had 1, 2, 3, 4, 5, 6, 7, 8, then for the inverse function, you would see that when you put in the outputs of the previous function, they gave you back the original inputs. And you guys should have seen that in that chart in your investigation, that you kept getting back the same values if you plug them into, the inverse function. Graphically, what you guys should have seen is that there is symmetry, specifically over the line y equals x. So that if this is a graph, and then this is where the line y equals x falls on the graph, that basically these points would stay and everything else would kind of be reflected over, try that again. Everything else would be reflected over that line. So we'll show you what that would look like. And then if you're doing this actually on a graph, something that's helpful is to actually use the fact that the x and y values switch. So if you see the 0.15 in the graph of the original function, you could graph 5, 1 for your inverse function. So we'd see something like this with that reflection, like it got folded over that line. And then lastly, algebraically, how we tell if something is an inverse is that if you compose them in either order, so if you do this, or if you do this, you should get back the original input. So f inverse of f of x should equal x, and f of f inverse of x should also equal x. And it's not that they should just equal the same thing, it's that they should specifically equal x, meaning if x is what you originally input and this function turned it into something, the inverse function then does something to it that turns it back into specifically the first value that you started with. And so if I gave you a function like y equals 3x plus 2, and I asked you to find the inverse, how would we do that? So we understand that graphically we could draw it and reflect it. We understand numerically that we could switch the points. We understand that when we compose the functions, they give us back their algebraic values. But how do I actually write the new function? And it's basically what you see with the numbers, but doing it in a more abstract way. So with the numbers, we said the x and the y values switch. So we're going to do that when we want to create an inverse, but instead of just switching one set of numbers for one specific instance, we're going to switch them so that we see it happening all the time. That y is now taking the place of x and x is now taking the place of y. And then to write the inverse, you want to take the fact that you've changed the equation and now you want to write it in the equation format that we normally do, which is to solve for y. So it says y equals. So I would subtract 2 from both sides and then divide by 3. So like my inverse here, so we switched x and y, and then we solved for y, and our inverse function is x minus 2 over 3. Or if you wanted to view it more like a linear function, like this. So in examples 1 here, to determine if each of these is a function, we have method 1, we're going to focus on composition. So this is kind of like algebraically trying to prove it. And then we have the graph, so we could try to graphically prove it with symmetry. So here, to algebraically prove it, we need to do f of g of x and g of f of x and see if both ways we end up getting x. So to do f of g of x, I'm going to take the f function and plug in the g function, which is x plus 4 over 3. So that will look like 3 times x plus 4 over 3 minus 4. So I'd get x plus 4 minus 4. So I'd get x. So f of g of x does equal x. And now I need to check that it works the other way as well. So g of f of x means I'm doing g of 3x minus 4. G of 3x minus 4 means 3x minus 4 goes into this x spot, plus 4 over 3. The 4's will combine. I'll have 3x over 3. The 3's will cancel, and I will have x. So method 1 worked. Okay, I proved that these are inverses by showing you that composition turns out to be the original input in both cases. Now we're going to go ahead and do a graph. So to graph 3x minus 4, I'm just going to put some points here so that I have enough points to guide my line to draw it straight. Otherwise, I'm not so great at drawing it. So there's f of x. And then g of x, this is like the same as 1/3 x plus 4/3. So 1 1/3 is like the y-intercept, and it's up 1 over 3. Or down 1 into the left 3. And then I'm going to put the line y equals x on there for reference so I can truly see if these are symmetrical about that line. And there you can see the reflections of each other. So I'm going to do it one more time for one more example for you here. So g of x and h of x. So if I'm going to again prove these ones are inverses, I have to do g of h of x and h of g of x, hoping that they both work out to be x. When I do g of h of x, I would be doing g of negative 2x plus 3. And so that will look like this. Right away, I can stop without even going on to the other one, because whether h of g of x turns out to be x or not, g of h of x did not equal x, which means I know right away they're not going to meet the inverse requirement. Okay, so these are not inverse functions. So previously we saw yes with 2 methods of proof. Here we're seeing no. And then let's look at what that would look like graphically. G of x is y equals 2x minus 3. So I'm going to put a y-intercept at negative 3 and a slope of 2. Again, you don't have to draw all these points, but I do to make the line straight on my graph. So there's that line. And then h of x is negative 2x plus 3. So I'm going to draw that on here. And so you'll see that these lines definitely have a relationship. But when I draw in that line y equals x, you'll see the relationship is not symmetry over that line. So you'll see that they aren't clear reflections over that line. Maybe if they were shifted a little bit and tilted a little bit, but not there. So that's examples of numerically and algebraically and graphically, how we could see if things are inverses and prove that they are. Okay, so for each function, we're going to find the inverse and state if it is a function. So when it's just a set of points like this, literally each point in the inverse would just have the inputs and outputs switched. And then remember, if something's a function, it would have to pass the vertical line test, or in other words, for every input, there can only be one output. So even though, okay, so see, the original one was not a function because it already had -1 going to -2, but then also -4. The inverse here is also not a function because it breaks that rule as well. Okay. For part B, if we were to quickly find the inverse by switching x and y and then solving for y, this would be our inverse. Okay. And now we have to determine if that's a function. So that is basically 1/4 x. So the answer there is yes. Okay. Now, an idea here is that you don't really have to know if the second function is a function to determine its inverse because of the graphical kind of method. So let me just throw this out there for you guys to see. If y is equal to 4x, it's a steep line like this. Okay. This line is a function because it passes the vertical line test. So when I test any vertical lines on here, this function will only hit twice. Okay. And that's, we made sure that for every x, we have one y. This is what the vertical line tests, okay? And that makes something a function. Then remember how we've been testing 1-to-1. For 1-to-1, you would want it to pass the vertical line test, but then also the horizontal line test. The horizontal line test is testing that for every y, there is one x. That's what it's testing when I look at those. This also passes the horizontal line test. The horizontal line test is actually a disguised way of doing the vertical line test for the inverse, even though you can't see the inverse. See how it took our vertical line test and just switched the wording so that x's and y's switched? That means the horizontal line test will be the same as running the vertical line test for the inverse. But you can run the test on the original function without ever seeing the inverse. So let's try to use that idea in the next one. So in the next example, if I switch x and y to find the inverse and then start solving, my last step here would be to multiply both sides by 2. So my inverse would be that y is equal to 2x minus 4. So again, two ways to tell my inverse is a function. This original function is a function, and it's 1-to-1. That tells me immediately that my inverse will be a function, or I can understand what the inverse looks like. Okay? Part D is slightly more complicated to solve for, so I'm going to switch the x and y. And I'm going to solve for y. It's in here, but all the y's are contained in a squared, so I'm first going to get that squared alone. Then I'm going to take the square root of both sides. I can't forget my plus or minus when I do that. So I'm going to have that y is equal to -2 plus or minus the square root of x plus 3. Okay. Now, is this inverse a function? The original is a function. A parabola is a function. However, the parabola is not 1-to-1 because it fails the horizontal line test, which tells me my inverse will not be a function. All right, we're going to talk down here about these graphs, and then I want to talk a little bit, a side note about domain and range, because that's important for you as well. So to sketch the graph, I'm going to put in that y equals x line. And again, remember this point will stay the same. And then if you're struggling, I would pick some points to help you. So see how the original graph here has this point 0, 2. That means your inverse graph will have 2, 0. See how this has 3, 0, then our inverse will have 0, 3. Okay? If you have to find something else, so this has a point very close to negative 3, 0, then our inverse will have 0, negative 3. Okay? So we'll see something like this. Okay? And you can see that the original is a function and the inverse is not a function because it doesn't pass the horizontal line test. Okay, and you can tell that by the original. So if we look at this one, if I go to draw the inverse, this point's going to stay. And then see how it has the point 3, 1? Then we expect the point 1, 3. And then see how it has the point 0, 4 on the original? Then we expect 4, 0. So in this case, the inverse ends up right on top of the actual line because it was already a reflection over the xy axis. Okay. So how can you tell if the inverse is a function? You should be looking at running the horizontal line test on the original. So the original function has to be 1 to 1 in order for your inverse to be a function. And then a small note about a unique situation that could come up. So let's say that your original function is the square root. So it looks like this, okay? So think about what the inverse would look like. Okay, if we took the inverse of that, it would look something like this, okay? If we solve for it algebraically, so if we switch x and y and we get y alone, notice it says x squared, but this isn't exactly x squared. It would be if it had this other portion here, but it doesn't have that. So the one note that I wanted to make, which will also be very helpful in the homework, is that not only are you switching x's and y's and solving for the y's, but it depends on the domain and the range of the original function since the x's and y's switch. So since the domain of the square root function is only 0 to infinity and the range is only 0 to infinity, even though I get this equation as my inverse, that's not wrong, but it's that equation, but only in the domain from 0 to infinity because the y's became the x's, so they're restricted the same way. And then the range would also be from 0 to infinity because the x's became the y's. So it's important that we pay attention to the domain and range and understand that they are just like flip-flopping the x's and y's, meaning what used to be the domain becomes the range and what used to be the range comes the domain. And the reason they're extra important is because if you looked at a function like this, you might think it looks one way, but it really is only a portion of it. You wouldn't know that without looking at the domain and the range. Okay? So the main goal here for you guys, I'm going to go back to the beginning, is that you understand that inverses actually have all these things in common, okay? So main skills, like can you identify them with numbers? Okay, do you see those inputs becoming outputs, outputs becoming inputs? Can you identify them graphically with that symmetry over y equals x? And then can you prove their inverses algebraically by composing them and showing that they equal x, and that's in both directions. In addition to that, you should know how to find an inverse, which involves switching the x and y. So all through the notes, we practiced that a little bit, and then there were two things on here that were kind of extra that we had to pay attention to. This idea of understanding if the inverse is a function, and that we can tell that by looking at the original function without even knowing the inverse equation. And then also that when we find an inverse, sometimes there might be this restriction on the domain or range based on how they were restricted originally, and that we should understand that the domain of the original function now becomes the range for the inverse, and the range of the original function becomes the domain for the inverse. So that's it, and that should help you with the homework.